recording right now too, so that we can.
So let me, first of all, let me go down. So what we're going to do, if we have raw data, which comes in a little bit later in the section, we're going to use our TI instructions to find the 5-number summary, which are here for you on slide 3 and 4 in here. And then you're going to use that to construct your box plot. But essentially, if you look at the example that she gave you, you have a bunch of raw data here, okay? And we're not going to draw the whole box and whisker plot because I don't think that was your question. Your question was, what do we do to find the interquartile range? So she does her calculator procedures, and the 5-number summary she gets are given here. This is the minimum, Q1 42.5, and so forth. The interquartile range is simply Q3 minus Q1, 50 minus 42.5, and that's 7.5. So the interquartile range for this example, or the IQR, would be 7.5. Now, we do these things, we use these things to find.
Oh, I'm talking about this now. This is the IQR that I got was from here.
Okay.
It's the difference between, and I just did the 5-number summary just like you did.
Mm-hmm.
That this is not the main reason I'm showing you this video, but it's appropriate.
Like the outliers, but again, that's not your question. The interquartile range is simply Q3 minus Q1. Now, we use this number to then calculate the bounds of what we would call normal or expected values using the upper and lower limits to figure out what our outliers are. So we take our IQR as part of our box plot situation, and we multiply the IQR by 1.5, and we then subtract it from Q1 and add it to Q3 to determine if we have outliers or not. Now, the other thing I wanted to show you, because the textbook does something else here that the examples in the slides don't show you. So let me show you that. And that is, it asks you for a bucket.
So we're looking at this here.
Identify the maximum.
So here's
minimum.
what the box plots look like. Here they've given you a box plot, and the instructions say use each box plot to identify the maximum value, the minimum value, the median, the first quartile, the third quartile, and the interquartile range. This is why I thought this video might be useful to you.
It would be, yes, Shauna.
So this first dot, if it's an outlier, you'll have a star. Okay, but because there are dots here, these are just the minimum and the max. So the minimum here is about 3, right? And the maximum here is about 11, for example, right? For number 7, right? Now, the Q1 is the sides of the box. The left side of the box, the lower quartile, right here is 5. The right side of the box is Q3, which is 9. Okay, and this line, sometimes it's in the middle, sometimes it's not. Okay, but this line in your rectangle is your median, which is 8, which tells us that this is a skewed distribution. This distribution is skewed. Let me
Okay.
continue.
The median, the first quartile, the third quartile, and the IQR. When you're looking at a box plot like this, the lowest value you have, so if you look at number
Here.
7, the lowest value you have is obviously the minimum, that's 3. The highest value you have is 11 over here. The edges of your rectangle, the left
And
edge
here.
here and the right edge here are Q1 on the left and Q3 on the right, respectively. So Q1 for number 7, for example, would be 5, and Q3 would be
Right here.
9. Once again, Q1 would be 5,
Right here.
Q3 would be 9. The median does not have to be in the middle. It just means that this distribution is skewed. So don't be thrown off by that. The median can be off center. It just means the distribution is not normal. Okay.
If this was a dot plot, there would be
This
more
middle
dots between the 8 and the 9, Shauna.
Ask me that again. If this were a dot plot, what?
There would be more values between the 8 and the 9. It would be saturated there.
It's okay. So that's a good question. So the center of the box, the way you figure that out, if I look at the actual middle of the box, the middle would be somewhere here probably, right?
Yeah.
And this median is to the right of the center. So this is a right skewed distribution. So there would be more values toward the right, whether they're between 8 and 9 or whether they're, but it's definitely past. The mid quartile is actually 5 plus 9 divided by 2, which is 7. So the mid quartile is here, and this is a right skewed distribution. I don't think I go over that in this particular, because the question in particular was, how do I do it? If I have just the numbers, how do I figure that out? So, but yes, they would have to, we don't know exactly where they are, but there's more values on this side. Whereas number 9, this is left skewed because the center of this box is about here, maybe, or at about 80, right? So this would be skewed this way because there are more values here, right? There are more values lower, so it's pulling it this way. So there's more values piled up on this side.
Number 10 is symmetrical, right? Or what is it? What would that be?
Well, I don't have number. I can't see number 10 unless I switch screens.
It's
I'll
right down the
go.
middle.
I'll go to the textbook, but I can't see number 10 from this screen.
It's
Let me
perfectly
finish.
centered, Shauna.
Let me finish playing. Yeah, then if that's true, then it's normal. Okay.
Normal.
Let me finish playing this.
But your IQR is the difference. It's essentially, it's the length of the rectangular
It's
portion
how
of your
far
box.
you go from
So
here
9
to here
minus
or
5
here.
is 4. The interquartile range here is 4. If you look at number 8, you have 225 is Q1, 300 is Q3. The interquartile range here is 75.
75.
300 minus 225. If you have data, as you do in the first questions here,
Right
find
here.
the 5-number summary as she did on the
I'm
slide.
talking about.
Find Q3.
I went back
subtract
to these now.
Q1. That's the IQR. Okay. Those skills you're going to use to find other things about the box plot. But I hope that helps you. I hope that answers your question about the IQR, and I hopefully will see you virtually very soon. Take care and be healthy.
I can send you the link for that later.
Yeah, that'd be great.
But that's, that was a little digression for that.
Especially because I have the book that you're working on, so.
Well, no, and I tutor for, so I can always send you the page and the screenshots, but that's definitely there. So do you want to go ahead and share your
Sure.
PowerPoints again?
Huh?
Okay, so this is chapter 3 now. We're learning about measures of distribution, okay? And finding outliers, the 5-number summaries in the box plot, and the measures of association between two variables. That's quite a bit to cover, okay? All righty. So the distribution shape, z-scores, Chebyshev's theorem, the empirical rule, and detecting outliers. So is there anything in particular that you want to have me go? I mean, I'll go over it, but is there anything in particular that you're having?
Probably not until we get into the measures of location and the measures of dispersion.
Okay, all right. So you're okay with shape, basically?
Yeah, I'm okay with shapes. I'll go over them, but I understand the concept enough so when I go over them, I can iron those out.
Okay, not a problem. And then here she gave you an example, right? And then she put it in the software, probably. Yeah, she put it in the software and she got quite a skew, right? Because that's what's expected. This is the formula. This is the same formula that I gave you earlier, just in symbols. So here it's saying the z-score of some I value in your data is that score, whatever that score is, whatever that data value is, minus X bar is the sample mean. So you have to know what the mean is for all your sample data. And you divide that by the standard deviation of the sample.
Right.
Okay. These are important for in terms of general understanding. So a z-score of 0 means that you're right at the mean, which makes sense because you're taking the score minus the mean. So if you get 0, you're right on it.
Okay.
A z-score that's positive means that your score, your raw, call it your raw score, your data value is above the mean. Because remember, it's your score minus the mean. So if the mean is lower than you, then your result will be positive. A data value less than the sample mean will have a z-score less than 0. So those are the significance of that. And then she gives you some examples.
So she takes the lowest value and the highest value, Shauna?
No, that she's saying to remember the formula is xi minus, this is not the high, this is not the maximum, this is X bar. So again, it would be helpful if she put the summarized data was here. But in this data set that she gave you down below, okay, the value that she's focusing on is if you're paying 425. So what she did here was, if you go back up to your previous slide where you had all of the data values for the apartments right here, okay? What she did was she took each of these values and she computed the z-score, okay? Now she didn't show you a couple of things here, which would have been helpful to you. So what you need to know is you need to know a couple of things which are down in the slide below, but they're not on this slide. So what you need to know is, you need to know the value that she's using. This was her example calculation, okay? You need to know how many values do I have? Okay, now, since she's doing the z-score for every data value, you can safely assume that the number of z-scores she has is the number of data values she has. And the reason you need to know that is for the average. So you have all of these 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have like 70, if I'm counting correctly. Okay. And what she did was she took the previous list, she put it in the calculator or the spreadsheet. To get the mean, she added it up and divided by 70. This 490.80
Mhm.
is your mean. So 70 values, the mean of all 70 was equal to 490.80. And the standard deviation was equal to 54.74. But she either got that from the spreadsheet or the calculator, but one of the two. And then what she did was, for every single value in her data set, the original data set, she computed the z-score, which you have down here. Now, it's hard to understand that because you can't look at the original data next to it. She did one example calculation. So for a rent of $425, Z equals what you see on the screen. The rent that you pay minus the mean, which she did by adding up all 70 and dividing by 70, and then the standard deviation, which she found to be 54.74.
Okay, so on an exam, Shauna, this information is going to be given. It's going to be the first one, but to get
Well, you have to, this is probably the data set
right,
that she's going to give you.
so I would have to enter all of these data set
Because, and
information.
then you would use your stat calc function or
To
your
get the
Excel
mean.
function to find, depending on what she's looking for. I mean, it'll give you both at the same time, but it won't give you the z-score directly. But it will give you the mean and the standard deviation, which you need for the z-score.
Okay.
That's the advantage of using spreadsheets, because it can do the calculation repeatedly and give everything to you at one time, where with a calculator, it can do it, but it can't give it to you all at once. Okay, now, when we talk, you said you were having some issues with Chebyshev's theorem, right?
Yeah, she had brought it up, yeah.
So the thing with Chebyshev's theorem is that has to do with shape to some degree and spread and the kind of data that you have. So if I want to talk about Chebyshev's theorem, let me stop sharing here for a second. I'm going to stop your screen share. And I'm going to share my whiteboard. And I'm going to introduce it maybe a little differently than she did. So when we talk about the Chebyshev's theorem, we're talking about a distribution rule. So we have to think about shape for a minute. Okay, now shape is one of the characteristics, and it can be normal, it can be skewed, right? It can be uniform. It can be other things, but these are some of the more common ones, okay? Now, before we talk about Chebyshev's theorem, I want to talk briefly about, want to remind you about the empirical rule, okay? The empirical rule only applies to
Distribution means.
Bell, well, that's true, but it only applies to bell-shaped normal curves, okay? And so do you remember the percentages for the empirical rule?
No, I don't.
Do you remember what I'm talking about, or you don't?
No, Shauna, I don't.
Okay, all right, let me start there. So let me do something here. Let me pull up this, I'm gonna pull up something here, just, and let's see, I'm going to downloads. I'm gonna pull up that because I want to show you.
You said the empirical rule only applies to bell-shaped.
Yeah, it only applies to bell-shaped curves. Now there's a reason. I'm gonna pull up something for you really quick. This is a lot of stuff and I don't necessarily want to give you the whole thing, but this, let me share what I have for you on the screen here. This is a picture of a bell-shaped curve with our percentages. Okay, now for the purposes of this lesson, I'm not interested in going through where this came from or how it came to be. You need to know that, but for the sake of your question, you don't need to know this right now. What I need you to focus on is that these percentages, okay, apply to bell curves. So if you look here, the mean is in the middle, right? So we have a situation where the mean here is in the middle, right here, right? The mean's in the middle right here. And your one standard deviation away on the right and on the left is 34 each. So that's 68% fall within one, right?
Yes.
And then if I look at another 13 and a half and 13 and a half over here, that's another 27. 13 and a half plus 13 and a half is 27. And if I add 68 plus 27, I get 95 down here. So 95 are within 2 and 99.7 are within 3. Now, where am I going with this? Well, that works for normal curves, okay? But Chebyshev's theorem is a little different. Chebyshev's theorem is a little more conservative because Chebyshev's theorem will work for any kind of distribution that you have. It can be skewed, it can be normal, it can be uniform. Chebyshev's theorem works regardless. So what I'm trying to do here is, there it is. Okay, so the empirical rule that I just showed you only works for normal bell-shaped curves, but Chebyshev's theorem is more versatile. It's also, it's more conservative, so it's not as accurate, but it gives us another kind of information. So Chebyshev's theorem uses different percentages than the empirical rule. That's why I wanted to show you that, okay? Chebyshev's theorem uses different percentages and applies to any shape. So it doesn't have to be bell-shaped to work, okay? To any shape of distribution. Okay, that's why I wanted to go there. Now, what happens with Chebyshev's theorem is that it's based on the number of standard deviations from the mean you are above and below, right? But what it says is that the percentage of data within K standard deviations of the mean is at least 1 minus 1 over K squared. 1 minus, oops, of the mean, hold on. Of the mean is at least 1 minus 1 over K squared, okay? So it depends on our distribution, okay? But if I said something to you like, suppose that there are 500 bean plants in a field. And their average height is 8 inches. Well, we'll do 9 inches. 9 inches with a standard deviation of 2 inches. Let's say, right? And I want to say, I want to ask you some questions. So first I want to ask you, find the interval in which the heights of at least 75% of the plants of the plants lie. Okay, so I need to do a couple of things here, right? What's happening is I don't know how this is shaped, right? But what I do know is that for the sake of understanding how the picture works, I always draw like, well, not always, but I usually draw like a little number line here. And I put my mean in the middle. So the average height is 9 inches. Okay, 9 inches. There's 9 there. Now, I know that with a standard deviation of 2 inches. So if I add 2 inches to 9, that's 11. So this is 11 here. And if I subtract 2 inches from 9, I get 7 here, right?
Right.
Now, this is within 1 standard deviation, within 1, because I went 1 above and 1 below, but it's within 1 standard deviation of the mean, right? This K here, this would be a picture of K equals 1, because I'm 1. Now, the formula is not going to help me much if K is 1, because Chebyshev's theorem means you have to be more than 1 standard deviation away, okay? And the reason for that is that Chebyshev's theorem says that the percentage is 1 minus 1 over K squared. Well, if K is 1, then you have 1 minus 1 over 1, which is 1 over 0, right? But that's what this would look like. Now, here's the thing. I don't know what this percentage is. It tells me 75, right?
Mhm.
So I need, in order to actually find, I want the interval, right? I want to know what these numbers are going to be. It's not going to be 7 and 11, but I want to know new numbers. I want to know what these numbers are, but I have to find how far apart am I? How far am I from the mean first, right? So before I can answer this question, I have to ask myself, okay, what is K? How many standard deviations from the mean do I need to be so that P, the percentage, will equal 75, right? Well, that's easier than it sounds, because remember, the percentage of data within K standard deviations is at least 1 minus 1 over K squared. So what we do is we say, all right, usually we use a decimal. So we go 0.75, my percentage, is equal to 1 minus 1 over K squared. Okay, that's my equation. All right, now if you do some manipulation here, do some algebra, you'll find out that in this case, K will be 2. K is equal to 2. I can take you through that algebra if you want, but it's this K value that you're interested in. So in this case, if K is 2, then this next value over here would be, remember, the standard deviation is 2 units. So this is 13, right? 11 plus 2, this is 13. And this 2 values below me would be 5. So according to Chebyshev's theorem, in this particular case, 75% of your bean plants, or a little less than 400 of them, would be between 5 and 13 inches tall, because there are 2 standard deviations from the mean. So the answer here is find the interval in which the heights of at least 75% of the plants lie. My answer here would be since K is 2, then the interval would be the interval from 5, and different books will show this different ways, but I'm going to show this with interval notation between 5 and 13. Okay, do you have questions about this?
So K represents the standard deviation, Shauna, in the formula?
Okay, be a little bit careful. That's what trips people up, okay? K is not the standard deviation. The standard deviation, and here, because I chose 75, that's why you think that. The standard deviation is 2 units. Okay, but K is how many increments you are away from the mean. So let me change this measurement. Let's say I change this measurement to let's say I change this measurement to 4 units right here. So I'm gonna draw this. I'm gonna say that this is 4 units. Okay, this is 4 instead of 2. Okay, so now in that case, this becomes, let me erase the bottom part of the drawing. The bottom part of this drawing here would be, I erased too much of it. Let me undo. Okay, so let me show you this. So now let me turn on my eraser and just get rid of this and get rid of this. And again, I wiped out the, okay, hold on. Let me undo that. Okay, so now if I erase this here, then I'm like right there. Okay, so now suppose that my drawing looks like this. Suppose now that in this case, I'm drawing and I have, here's my line, right?
Mhm.
My mean is still
9.
My mean is still 9. Okay, but my height, I mean, my standard deviation, this is,
4.
yeah, hold on. My pen is not responding as it should. And I'm using the mouse, so sometimes I get a little delay in there. But this is 9 units, okay? Now, this is, the standard deviation is 4 units, right? So now I have to count by 4s. I'm counting by 4. So I'm counting by what the standard deviation is, okay? So in this case, if I'm counting by 4, 9 minus 4 is 5, right?
And 13.
And this is 13. But now here, K is 1. Because I'm 1 standard deviation below and 1 standard deviation above, right?
Mhm.
If I wanted to be 2 standard deviations, then I would have to be at 1 and 17. You see that? You see the difference? So K is the number of times, if this is the mean here, okay, K is the number of times you move from the mean on either side. Here's the mean, I moved twice. K is 2. But how many units apart are they? They're 4 units apart. So the standard deviation is how many units you move. K is how many multiples of the standard deviation you use. The percentage of data within K standard deviations. K is not the standard deviation. K is the number of times you increment. Okay,
How many jumps you take?
right, on either side.
Okay.
So K is not 4 here. K is only 2. You went 2 on either side of the mean,
Mhm.
right? So let me show you something else.
Isn't K four in the standard deviation?
No, because it's within on either side. So it's 2 on either side. So it's within 2. 2 on either side. It's like saying, I live at 14813 Cameo Avenue. That's my address.
Mhm.
Okay. If I go within 2 blocks of my house, I could go 2 blocks east of me, 2 blocks west of me. That would be a 4 block span, a 4 block interval, right? But it would be within 2 blocks either direction because my house is in the middle.
I see.
Does that make sense? So
Yeah,
K would be 2. K is not 4. K is not the width of the interval. K is how far you are from the middle of it. Okay, that's the one thing that usually trips students up more than most other things is the difference between K and S. S is the standard deviation. K is how many times you move. That's the tricky part. And that's a place to get stuck because people do, and there's nothing shameful about it, but that's the difference. That's always the discussion.
Thank you, Shauna.
Every semester, that's kind of the discussion point that happens. Now, let me show you something here from our favorite book today. I don't know, let me pull this down so I can do a Chebyshev's theorem is in chapter 3, either 2.7 or chapter 3, but I think it's in chapter 3. And I want to say that it's in 3 point, could be at the end of this. Is it at the end? 2, or is it at the beginning of 3? We'll find out. Sample variance. Let me do something here.
On page 134, Shauna.
Yeah, I have, I was 3 pages too far. So it's right here. There it is. So let me go back to this part. Let me bring it up. Just see. And then we'll look at this here. So right here, we have, no, 34. The square root of, no, that's covariance, sample variance, population variance. I think it's in 3. Okay, hold on. Let me see. B.
Chebby.
There it is. So this is, I was talking about the coefficient of variation. But Chebyshev's theorem, it's actually a little different in the ebook. The page is a little bit different. It's on, it's at the bottom of page 138 for me, but here's what it says. Let me make it larger. So we'll make it that. Okay, so Chebyshev's theorem, developed by a Russian mathematician, specifies the proportion of the spread in terms of the standard deviation. Okay. Now, here's where, if you need help to see where the 2 came from in my example, okay, they do the math for you here. When K is 2, the percentage is 1 minus 1 over 2 squared, which is 1 minus 1/4 or 75%. Okay, now here's an example. Okay, so it says variable 1 has a mean of 70 and a standard deviation of 1.5. Okay, so what this is saying is that we have a mean of 70. So I don't draw the distribution because I don't know what the distribution looks like, but the number line will help me. So I put the mean in the middle, because for our purposes, it doesn't matter where the mean is. We just have to know how many times we're moving it. So the mean is 70. Okay. And the standard deviation is 1.5. So 70 is my mean right here, right? And I'm moving 1 standard deviation to the right. Okay. So the standard deviation, remember, is 1.5 for this example, right? So 70 plus 1.5 is 71.5. 71.5. Now, hold on, let me erase this. So this is my so this is going to be that one and that one. That's one standard within 1 standard deviation. Okay. And those values are 70 minus 1.5, which is 68.5. This is 68.5 on this side. 68.5. And my other side is 71.5. Now, here, this distance is 1.5 units. This distance here is 1.5 units between 70 and 71.5.
Okay.
That's your S, that's your standard deviation. Okay, but my K is 1 unit. K would be 1 here. Because I moved 1 unit, 1 multiple of the standard deviation on each side. Does that make sense?
Okay, but if K was the 1 unit, like you said before, then it would be 1 minus 1 over 1.
Right. So the formula doesn't work for 1, right? Because that's what it says here. where K is a number greater than 1. For obvious reasons, because 0 would not make, that doesn't help us, does it? But if you're gonna do it this way, if you're gonna draw it this way and do it, you have to increment it first. Now, they asked us for 2, didn't they?
Yeah.
See? So what we would do is see these numbers in black. We're gonna do another piece to this. We're gonna do a piece out here, right here, and another one right here on the left. Okay, now those 2 pieces are going to be 68.5 minus 1.5. So that's going to be 67. So this is going to be 67 under, not 97, 67. And this is going to be 1.5 more. So that's going to be 72, right? Now, I did it by doing the arithmetic just to show you. They did it in a little more compact way. They said, well, I'm doing 2 marches from 70 and each of them is a half a unit, 1.5 units. So I'm going to take 70 plus 2 times 1.5. And I did the wrong arithmetic. This is 73, not 72. So ignore me.
Okay.
This is 73, not 72 units. But this is my point in showing you this is
Oh, I see.
that
No, Shauna.
there's a difference between S. S is 1.5, but K is 2. Do you see why?
Yes, because of the standard deviation, right?
Right, because I moved twice. So I moved, here's 70 right here. Let me try in green. I moved here 70, right? I moved once and I moved twice. This is 2 units. 2 multiples of the standard deviation that I moved on either side of the mean. Once here and once here. So a total of within 2, as I said. Within 2, there's 70, there's 2 marks on either side. But each of those marks is 1.5 units apart.
And I can see that in the problem here where it says 66, 67, and 73.
Mhm.
All between.
Yeah.
Okay. Thank you, Shauna.
Does that help a little bit more?
Yeah, a lot. Thank you so much.
We can do some, you want to do some more tomorrow? You want to set up a meeting for tomorrow?
Yeah, that'd be great, Shauna. That'd be
Okay, I'll check with Irma and see what time she wants to come in, and I'll just take the both of you back to back then.
Tell her I said hi.
Oh, yeah, no, we're gonna be writing